Hey everyone, this is Abby. I just wanted to go over the last problem on recitation worksheet number 15 because I think that was probably the trickiest and most intense question that we had on Tuesday. I'm going to break this problem into two separate videos. The first being just going through writing the rate law equations for all of the mechanism steps, and then in the second video I'll go through all of the math involving like the substitutions of all of the equations, just in case you're only interested in the first part or maybe need a break in between the two videos, since I know this question involves a lot of math and thinking. So feel free to pause at any point, skip between videos, etc., whatever you need to do to help you get through this worksheet problem. So we're going to go ahead and get started. And when we're dealing with these types of mechanism problems with rate laws and the fast and slow steps, we want to notice a couple things. And probably the most important one is that you'll notice that each of the individual mechanism steps has a description of whether or not it's fast or slow. And typically for these mechanisms, we'll usually have only one slow step. It may or may not be the last one. It could be the third one, the first one. It really doesn't matter the order in which they're fast or slow, but it's this slow step that's what we call our rate determining step. And so that's the equation that is really going to dominate our overall rate law, and that's going to be our main one that we're substituting all of the faster rate equations into. So this last one is going to be super, super important. So we're actually going to start off by writing the rate law for the last step, which is our rate determining step, and I'll just note that right here. So we're going to write that rate law. And there's a couple reasons why we want to start with the slowest step, and we'll get into that right after we determine what that rate law is. So our general form is that we have the rate, and sometimes we write it as this sort of curly V letter, and that's going to be equal to some rate constant. In this case, it's going to be K5, because that's what we have above the arrow here. And then we're going to multiply all of the reagents. And the reagents are only the ones that appear on the left side of the reaction. So that's going to be K5 times the concentration of A times the concentration of E. So that's our rate law for our rate determining step. And the reason why we do the rate determining step first is because when we're writing rate laws, we only want reactants in our rate law. We don't want any intermediates or products. And so if you'll remember from earlier on in this worksheet, we had our overall reaction, which I'll just write in a different color. It was 6A plus 3B goes to 6C plus 2D. So our only reactants for this overall chemical equation are A and B. So those are the only ones that we should see in the overall rate law. We don't want any intermediates and we don't want any products. So the reason why we start with our rate determining step is to see if we have any of those intermediates or products in our rate law. And we actually do, in fact, have one of those. So E right here is one of our intermediates. That was in part of the instructions here. E, F, and G are intermediates. And then going back to our overall equation, C and D are products. So just keep in mind that A and B are the only ones that should or could show up in our final rate law. And anytime we have E, F, G, or C or D, we're going to use these other mechanism steps and those rate laws to try and get rid of them. So because we have this intermediate E here in our rate law, we're going to need to figure out the rate laws for all of these other faster mechanism steps so that we can substitute them in one at a time to get rid of any intermediates that pop up once we start doing this substitution. So we're going to go ahead and start writing these rate laws. And what you'll notice about each of these faster equations is that all of them have these sort of funky arrows. And I'm not sure exactly where lecture is in terms of these types of reactions, but these funky arrows are what we call equilibrium reaction arrows, and that means that there's a forward reaction indicated by this top arrow, and that forward reaction is happening at the same time as a backwards reaction, which is that sort of half bottom arrow. And that means that in the forward reaction, we have reactants that are on the left, but if we have the backwards reaction, that means that C, E, and G are now our reactants. And so because we have both of these reactions sort of competing with each other, they're both happening at the same time, we know that their rates are equal to each other. And I have this note in hot pink up here. So the rate of that forward reaction is actually going to be equal to the rate of the backwards reaction. And so that's going to be really helpful because, and I'll just get rid of some of this mess here. So we're going to start writing this, this rate law here. So we're going to start with the forward reaction. And that is going to have it's going to take the same form as the equation that we did for the rate determining step below. It's going to have a rate. It's equal to a rate constant times the concentrations. So we're going to take the rate constant, and that's K1 for the forward reaction. And then it's multiplied by our first reactant A, and that's going to be to the second power because of that coefficient 2 that's out front of it. And then that's going to be multiplied by the other reactant F. And now this is the rate equation for the forward reaction. It's equal to the forward rate. Now we're going to set that equal to the same equation just for the backwards reaction. So instead of K1 as the rate constant, it's going to be K minus 1 because now we're going from right to left. So now the products that were in the forward reaction now become the reactants in the backwards reaction. So we have our rate constant times concentration of C times concentration of E times concentration of G. So that's our rate law for the first fast mechanism step. And we don't have to worry about rearranging these right now. This first video is just going through determining what these rate equations are, and then we'll get into the substitution steps in the next video. So if you feel pretty confident with the substitutions, you don't have to watch that next video if you don't want to, but it is there for whenever you need it. So now this second equation, which is also a fast step, also has those equilibrium arrows. So we're going to do something very similar to what we did in the first step here. We're going to have our rate equation for the forward reaction, which has a rate constant K2, and now there's only one reactant. It's just A. And we're not going to do any superscripts because there's nothing out front here, so we assume that it's a 1, and we don't typically write the superscript of 1 because it's kind of just implied. So now that is going to be equal to the rate of our backwards reaction, which has a rate constant of K minus 2. And now the reactant of that is just the concentration of C. And again, there's no coefficient, so there's no superscript in this expression. So that one wasn't too bad. So now we're going to do the rate expression for the third fast equation. So again, we have K3 as our forward reaction rate, and the reagents are A, and now again we're going to do to the power of 2 because of that coefficient there, and then it's multiplied by the concentration of B, and that's equal to the backwards rate constant times the concentration of C times the concentration of D. And then our last equation with K4 and K minus 4, our forward reaction is K4 times B to the second power because of that coefficient out front in B times the concentration of G, and that's equal to K minus 4 times the concentration of C times the concentration of D times the concentration of F. So those are all of our rate laws. And we wanted to use all of these because our rate determining step, which is this last one, it's in the form that we want, but it has an intermediate here. And intermediates are generally something that's formed as a product in an earlier step in the reaction and then almost immediately used up as a reagent. So first it's a product, then it's a reagent. And so because when we write the overall reaction for this, it appears on the left and the right side of the reaction, that's going to cancel out. So it won't appear in like the final chemical equation, but it does appear when we write out these mechanism steps. However, they have no place in our overall rate law expression, and so that's why we need to go back, write the rate laws for the individual steps, where they are going to include some of the intermediates here, like E and G, some of the products here, like C. We're going to use those and manipulate those a little bit to get rid of E and the other intermediates and products that will eventually be in that reaction because of some of our substitution steps. So that is how to write the rate laws for these. So I am going to stop the video. Feel free to take a break, take a breather. I know that was a lot, and get ready for a little bit of algebra in the next video. So I'll see you there.